Our mistakes are becoming gateways to new discoveries. We once believed Enceladus was just a frozen, lifeless moon drifting through the void, but new data has proven otherwise. Two different explanations have just been found for the paradox discovered by the James Webb Telescope objects that seem to break the very laws of the universe. One of them involves quasi-stars, strange giants, born when primordial black holes consume their own light. Meanwhile, a scientist has unexpectedly helped uncover new clues about Jupiter and Saturn. Let us step into a journey to explore the paradoxes tearing apart cosmic logic, where science rewrites history and the silence of space suddenly echoes like a challenge to humanity here and now. Before knowledge, there was curiosity. Before equations, there was a question carried on the breath of the night. What is this vastness above us? Every scientific truth begins not as certainty but as hesitation, a pulse between what we can measure and what we can only feel. The universe has never promised clarity. It only offers light, and even light arrives late. The photons that touch your eyes tonight began their journey 13 billion years ago, when the Milky Way was still forming, when continents were magma and oceans had no names. We stand together beneath a sky older than language, our instruments trembling against the silence. The James Webb Telescope hums softly. Its golden mirrors breathe the oldest starlight. For a moment you feel the planet turning beneath your feet, a slow heartbeat, beneath the hum of the cosmos. You realize every discovery is an act of faith disguised as precision. Science grows from this faith in observation in numbers, in the idea that patterns can be trusted even when the mind cannot yet see the full design. The cosmic microwave background, the spectral lines of hydrogen, the faint pulse of an exoplanet's transit. Each is a clue carved from darkness. Yet for every answer uncovered, 10 new uncertainties bloom like nebulae. Imagine you are drifting through that nebula. Dust swirls around you, glowing her red and blue, the wavelengths of birth. Somewhere within that haze, gravity begins its slow, invisible work and a star ignites from the collapse. This is the rhythm of knowledge: collapse, ignite, illuminate. Doubt is not a flaw, it is the force that shapes comprehension. Without it, there would be no reason to build another mirror, to send another probe. When Edwin Hubble measured the redshift of distant galaxies, he did not end a question, he created one large enough to hold all others. Let the weight of unknowing settle gently on your chest. The stars above you are not answers, they are invitations. The universe does not ask for belief, it asks for patience. And as long as we keep wondering, it will keep revealing itself one uncertain heartbeat at a time. Doubt is only the first breath of understanding. Every question once born begins to look for a shape, a pattern strong enough to hold its own uncertainty. That is how models are born, our way of drawing the outline of infinity, of turning chaos into curves and constants. Each model is a promise, an elegant shape suspended above the unknown. We trace equations across chalkboards, spin universes inside supercomputers and call the result truth. But they are not the cosmos, only its reflection trembling in thought. You and I live in an age of extraordinary confidence. The LCDM model sketches the universe with mathematical grace. It tells us that 13.8 billion years have passed since the Big Bang, that dark matter, dark energy, and ordinary matter weave together like unseen threads, shaping galaxies, bending the path of light, stretching time itself. With these numbers, we can predict the birth of stars, the faint afterglow of the cosmic microwave background, even the slow drift of galaxy clusters toward the horizon of the observable sky. And yet even this grand architecture trembles. The James Webb Space Telescope peers deeper than any eye before it, and what it sees does not entirely obey our laws. Galaxies too bright, too massive, too soon born within a few 100 million years of creation. By our equations, there should not have been time, but the data, quiet and stubborn, disagrees. Imagine standing beside Webb, its golden mirrors open like petals of a machine that listens to time. Every photon it gathers has crossed billions of years of expanding space, its colour stretched red by the universe's long breath. You look at that faint smudge, a galaxy flickering at the edge of perception, and realise everything we know may need rewriting. A model is only a map. When Galileo turned his telescope toward Jupiter, the moons he saw shattered the geocentric sky, proof that even the most elegant maps can fail. Centuries later, our maps are digital simulated, woven from the densities of cold dark matter and the equations of dark energy. They are beautiful, predictive, convincing, and yet one anomaly can undo them all. In a desert, if the compass fails, you still have the stars. In cosmology, anomalies are those stars, the limits of direction, the edges of comprehension. The faint red points Webb has seen, the so-called small red dots, whisper that something in our equations is missing. Perhaps the behaviour of dark matter, perhaps the tempo of cosmic structure, perhaps something stranger still. Picture the universe as a vast symphony. Each law of physics is a note, each silence a chance to listen. For centuries we thought we knew the melody, but Webb has heard a discordant tone, a rhythm that doesn't fit the score. We can ignore it or listen closer and rewrite the music. Science thrives not on perfection, but on contradiction. When a model explains everything, curiosity begins to fade. The cosmos reminds us gently, endlessly, that knowledge must remain porous. So drift a little closer in thought. See Webb glimmering beyond the moon's orbit, Earth turning below small, bright and restless. Above it, the first galaxies shimmer like embers of a fire that never truly went out. You can feel the tension between belief and evidence, the same tension that drives all discovery. Let that feeling stay for a moment. The models will change as they always do. But the sky remains patient, waiting for us to ask better questions. And so the models fade into the quiet. What remains is you, the observer. The equations have done their part, tracing elegant curves across invisible space. But every discovery begins again in a human eye. You stand in the dim control room of an observatory. The instruments whisper, cooling fans hum like distant seas. On the screens, the light of a 13-billion-year-old galaxy spills into graphs, curves, and colour maps. Yet before it becomes data, before it can be fitted into the next simulation, that light must first touch awareness. It must reach you. In that instant, the boundary between measurement and meaning dissolves. The telescope does not truly see, it only collects. It is your mind that translates numbers into wonder. Without a witness, the universe would still expand, but in silence. Scientists call this the observer's frame, the necessary reference from which all reality is described. In relativity, motion and stillness depend on it. In quantum mechanics, observation collapses uncertainty into fact. Even across cosmic scales, the same truth echoes. To measure the universe is to be entangled with it. Imagine drifting beside the photons themselves. For them, there is no time, only the endless corridor of space. They were born in the heart of a star, escaped its storms of plasma, crossed the cold gulfs between galaxies, and finally fell into your telescope. In their frame, that voyage took no time at all. For you, it spans nearly the history of everything. The difference is observation. We often picture the cosmos as separate, a vast theatre, and us the audience. But the deeper science looks, the thinner that curtain becomes. You are made of the same fabric that bends and stretches across billions of light years. The carbon in your breath was forged in stars. The iron in your blood once drifted through supernova dust. Each inhalation carries atoms older than Earth. You do not merely look at the universe, you continue it. Step outside the observatory. The air is thin, crystalline. Above you, the Milky Way arches like a frozen river of light. Each spark is a system of storms, gravity, and time. If your hand could reach that far, it would disappear among those suns. Yet the light you see is real, touching your eyes now, completing a journey that began before language. The human brain, small yet luminous, can hold these immensities. It can picture galaxies larger than imagination and particles smaller than thought. Inside its folds, electric signals echo the rhythm of cosmic radiation. Neuroscientists call it pattern recognition. Philosophers call it meaning. Perhaps they are the same thing. When the ancients looked upward, they saw gods. When we look, we see laws. Both are ways of reading the same text written in light. Our instruments, Webb, Hubble, Alma, are the eyes of that same curiosity, extensions of the oldest human impulse to witness. But even perfect observation is never pure. The mind projects, interprets, hopes. We smooth the noise, fill the gaps, draw constellations out of chaos. Doubt returns softer now, more like dialogue. The universe asks, "What do you see?" And we answer with imagination. Perhaps that is the final truth. Observation is creation. Every time you look at the sky, you redraw its meaning. The galaxies existed before you, yes, but their story began only when someone decided to listen. The night of thought fades into the morning of measurement. We have listened long enough to feel the universe breathing with us. Now we begin to count that breath. Every wonder must at some point touch a detector, pass through a lens, become a number. And yet the instant we measure, mystery rearranges itself. This is where imagination meets discipline, where the sky begins to argue with our equations. You stand beside the golden flower of the James Webb Space Telescope, its mirrors catching a dawn that left its stars billions of years ago. The hum of the instruments is low, steady, a heartbeat filtered through metal. Beyond the panels, the first photons of creation slide into sensors, ancient travelers finally arriving at our doorstep. Each photon carries a story, wavelength stretched by expansion color, reddened by time. When the first images arrived, astronomers expected only faint traces of infant galaxies, soft clusters still learning to shine. Instead, they found small red dots, impossibly bright, impossibly massive. The early universe, it seems, had hurried its own birth. These points are tiny on the screen, yet colossal in meaning. If the Milky Way were a football field, each early galaxy would already be the size of a stadium built less than a minute after kickoff. According to the LCDM model, that should be impossible. Matter needs time to cool to collapse to ignite, yet here they are, full-grown giants in a cosmic cradle. We expected lullabies. Instead, we heard thunder. Teams checked the data again, questioned the calibration of Webb's near-infrared camera, but the spectra held. The redshifts were real. These galaxies, if galaxies they are, existed when the universe was only 500 million years old, less than 4% of its current age. Imagine standing on a shore, tossing a pebble and watching it rise into a mountain before it lands. That is what the data implies. Some propose that these are not galaxies but blazing black hole nuclei, matter spiraling into darkness. If so, they should roar in X-rays. Yet they burn red and silent embers that refuse to scream. You lean closer to the monitor. Each pixel is a question, each graph a heartbeat. How could such complexity bloom so soon? Did gravity behave differently at the beginning? Was the recipe for structure rewritten in the first few 100 million years? Simulations run billions of digital particles evolving under known laws, but the models stumble. They cannot grow galaxies this fast without breaking physics itself. A paradox shimmers between what is seen and what should be possible. Picture the cosmos as a clock. For decades we trusted its rhythm, tick by tick, stars forming, merging, dying. Now Webb shows gears spinning faster than expected, some slipping out of sync. Perhaps the universe was more efficient than we thought, or perhaps our clock is wrong. Make it tangible. If 1 second of your breathing equaled a million years, the starlight reaching us now began while the universe was taking its first breath. You're standing metaphorically in the first second of creation, holding evidence of galaxies that should not yet exist, as if a child were born already grown, speaking physics we have yet to learn. Across the world, observatories hum with quiet astonishment. At Mauna Kea Paranal and Atacama telescopes turn toward the same faint coordinates. The data gathers like whispers layered into a symphony. Some hear the promise of new physics, others a call for patience. The contradiction remains beautiful and sharp. Science thrives on such discomfort. Every paradox is an invitation. The small red dots do not threaten our understanding. They reveal its edge. Even the clearest equations are only scaffolds built so the mind can reach higher. Breathe once more. Imagine floating far above Earth, watching Webb drift in the black. Below, the planet turns small, bright, restless. Above, the universe stretches without sound. Between them, a fragile mirror gathers ancient light, and hidden inside that light is a new story, one that refuses to fit. The paradox still glows on the screen, those small red dots defying every law we trusted. To understand them, we step backward in time into the universe's first hour, when gravity was still learning the rhythm of creation. What if these lights are not intruders, but pioneers? What if we are watching the first galaxies being born? You stand 500 million years after the Big Bang. The cosmos is opaque, with leftover hydrogen mist, a fog before sunrise. There are no constellations here, only clusters of gas trembling on the edge of ignition. Temperature, density, and time dance in fragile balance. From this chaos, the first stars emerge, colossal beings of hydrogen and helium. Astronomers call them population 3 stars. They burn hotter, shorter, brighter than any stars to come hundreds of times the mass of the Sun, yet living only a few million years, their deaths scattering carbon-oxygen ion, the seeds of all later worlds. If these ancient furnaces truly lived, then perhaps the galaxies in Webb's images are their descendants, the first cities of light caught in the act of assembly. Each red dot could hold billions of newborn suns sculpting themselves from primordial gas. From afar, they look like faint smudges. Up close, they would outshine constellations. Their glow is red because the universe itself is stretching, pulling light into longer, softer wavelengths, the signature of distance, the mark of expansion. We call it cosmological redshift. The farther the object, the redder its light. These galaxies sit at the very edge of detection, with redshift values beyond 10, even 13. Their light began its journey when the universe was less than 400 million years old. Now pause. Imagine that distance. If the Milky Way were a single grain of sand, these galaxies would lie beyond an ocean larger than the Pacific, beyond the curve of the world, beyond every tide. Their light has travelled 13.4 billion years, whispering across time we were here first. Scientists built simulations, dark matter halos condensing under gravity, baryonic gas cooling stars igniting. The models came close but not enough. To match Webb's brightness, star formation would have to be 10 times faster than predicted, as if a city built skyscrapers overnight when its blueprints allowed only tenths. Maybe nature was simply more efficient. Perhaps turbulence or magnetic fields helped gas cool faster. Perhaps early black holes recycled their energy-kindling bursts of starbirth like cosmic gardeners. Every anomaly hints at a new mechanism waiting to be written into the equations. Picture one nascent galaxy, call it Aurora. Only a few thousand light-years across, smaller than the gap between the Sun and the galactic centre. Inside it, tens of millions of suns ignite at once. Their light pushes against the hydrogen fog like dawn breaking through clouds. This is the epoch of Orionization, when the universe becomes transparent because its children have learned to shine. The thought comforts us. It means the laws still hold if stretched thin. But part of us hesitates. Could galaxies really mature so quickly? Could cosmic infancy carry such intelligence in its fire? The data whispers both yes and no. The colours match young stars, but the brightness defies expectation. It's as though the early universe was not a patient painter, but a reckless sculptor shaping masterpieces before it knew what art was. You look again at the infrared images. The red points are tiny, but imagination enlarges them. You drift through clouds of glowing hydrogen, past supernovae blooming like flowers, past rivers of dust where future planets will form. The silence feels sacred. The light touching your eyes began before Earth had oceans, before any creature had eyes to see. Perhaps these are the first galaxies, the first organised defiance against emptiness. Perhaps the universe in its youth was impatient to witness itself. And if that is true, then every photon Webb collects is not merely data, it is history's heartbeat, arriving late, but still alive. The thought lingers. If those small red dots are not galaxies born too soon, then perhaps they are something older, darker, and far more mysterious. Light, after all, can deceive. Sometimes what we see is not creation but consumption. Every galaxy has a heart. Some beat quietly, others roar. At their centres dwell the most extreme objects known to physics, black holes millions, sometimes billions of times the mass of our Sun. They are invisible, yet their gravity sculpts the architecture of the cosmos. When matter spirals inward, friction becomes fire and the void ignites. We call this an active galactic nucleus, a cosmic engine bright enough to outshine its host galaxy. Perhaps the small red dots are not infant galaxies at all, but these furious hearts in their first awakening. Picture it a compact core where gravity folds light back upon itself. A disk of gas, millions of kilometers wide, glows in infrared like molten metal. Jets of charged particles erupt from the poles, streams longer than the distance between Earth and the Sun. From this distance, such violence shrinks to a single pixel, a red ember floating in a cosmic sea. On Earth, telescopes like Chandrayaan New Star hunt for such engines in X-rays. Normally active nuclei shout across the spectrum X-ray ultraviolet radio. But Webb's new sources whisper. They burn deep red, almost silent. If black holes drive them, why are they so quiet? You stand in a dim lab at the Space Telescope Science Institute. Screens bloom with graphs, infrared, flux, spectral lines, luminosity curves. The shapes are familiar, yet something's missing. No X-ray peaks, no roar of radiation. Only the hush of data too gentle for its own power. Too young, someone murmurs. Too soft, another says. Maybe these are not violent quasars, but protoquasars, black holes still learning how to feed. To follow them, we travel back again 500 million years after the Big Bang. Matter is thick, gas clouds are warm, massive stars live fast and die hard, collapsing into seed black holes, hundreds or thousands of solar masses. Given time, they merge and swell into giants millions of times heavier. But that evolution should take hundreds of millions of years too long for what Webb now sees. So theorists draw shortcuts. One idea: direct collapse black holes born not from dying stars but from entire gas clouds collapsing straight into darkness. No explosion, no delay, just instant gravity. Such seeds could begin their lives already weighing 100,000 suns. If those existed, Webb might be catching their first meal's accretion disks still faint, their X-rays smothered by cocoons of primordial dust. The energy leaks in longer waves, glowing red instead of blue, silent instead of screaming. Imagine hovering above one. The gas spins faster than any hurricane could dream, temperatures climbing into the millions. Yet in the infrared it looks serene, a deep ember behind smoke feeding in secret. Even a modest black hole here would dwarf our solar system. Its event horizon could swallow the orbit of Pluto whole. Drop a photon near its edge and it would never return. 1 billion Earths could vanish inside, and from 13 billion light-years away it appears no larger than a pinprick. We try to simulate such monsters, spinning disks, feeding rates, radiation feedback, but the equations strain. To grow 1 billion solar mass black hole in 500 million years matter must fall continuously at the Eddington limit, as if a child became an adult in a single day. Unrealistic, and yet the evidence glows quietly in Webb's view. Perhaps we are missing a piece. Maybe gravity itself behaved differently in the dense early universe. Maybe dark matter guided the collapse, shaping invisible rivers that fed these newborn abysses. Others imagined feedback loops of dust and radiation, the cosmos building engines faster than our physics allows. Each theory bends under its own weight yet refuses to break. Light that should not exist reaches us anyway. Darkness that should scream remains silent. It is as if the universe, even in its infancy, already knew how to balance extremes, creation and destruction folded into one breath. Look again at that single red point in the dark. Behind it may lurk a black hole millions of times the sun's mass wrapped in matter, spinning faster than thought. Stand too close, and time itself would stretch seconds, becoming years, your heartbeat slowing until eternity felt near. And yet here on Earth, all of it fits inside a screen. The glow is gentle, numbers scroll, the paradox endures, majestic, unsolved, alive. The paradox hums on, quiet but unyielding. We have watched the small red dots through the golden eye of James Webb, asked if they were galaxies or black holes, and the universe has answered only with silence. So we listen again deeper this time, following the faint trail of colour that connects the ancient to the familiar. Perhaps these red embers are not strangers at all, but younger versions of something we already know. You stand inside the control room of Gemini South Observatory in Chile. Outside, the desert air is sharp and clear. The Andes rise like frozen waves beneath the stars. Inside, screens bloom with spectral lines, thin ribbons of colour holding the fingerprints of galaxies. The same infrared light Webb captured now passes through Gemini's spectrographs, revealing an unexpected kinship. Astronomers call these later objects blue dogs, dust-obscured galaxies. 2 to 3 billion years after the Big Bang, they forge stars at furious rates, their cores veiled in silicate and carbon dust. When that dust re-emits absorbed radiation, it glows bluish, almost electric. Then came the surprise when their spectra were laid beside those of the small red dots. The curves matched almost line for line. It was as if time itself had painted the same portrait twice, once in infancy, once in adolescence. Imagine walking through that timeline. The red dots are newborns, compact, radiant, impatient. The blue dogs are their older kin, larger, dustier, already shaped by feedback and gravity. Billions of years apart, yet their light hums in the same chemical rhythm. Strong hydrogen alpha, mid-infrared peaks from heated dust. Faint absorptions from freshly forged metals. In human terms, it is hearing the same heartbeat at 2 different ages. The emerging idea is elegantly simple. What Webb sees are not anomalies, but ancestors. The small red dots may be the early phase of galaxies that evolve into blue dogs. The paradox dissolves. Galaxies did not form too fast. They merely changed costume, trading the red cloak of infancy for the blue mantle of maturity. To test this, researchers used the Gemini multi-object spectrograph and cross-checked against Webb's NIRCam data. They searched for emission ratios of oxygen-3 hydrogen-V and silicon-2 signatures of violent starbirth. The match was uncanny. Both groups formed stars at more than 100 solar masses per year, while our Milky Way manages barely 1. Yet science asks for more than resemblance. Could such ferocious growth persist across billions of years? Simulations whisper yes if those early galaxies lived in overdense regions, where dark matter halos pulled gas inward like cosmic whirlpools. Gravity would feed the fires, radiation would sculpt the dust, supernovae would enrich the clouds, shifting colour from deep red to ultraviolet blue. Think of it as cosmic seasons, spring the red age hydrogen blooming into stars, Summer the Blue Age metals, rising dust thickening. Autumn the present, where galaxies mature and slow. And beyond the physics lies feeling. When astronomers compare these epochs, they sense continuity, the quiet realization that light is a diary written in changing handwriting. Now drift inside one of the blue dogs. Clouds of carbon dust tower like mountains. Each grain is a seed of future worlds. Around you clusters of suns flare, heating the dust until it glows in mid-infrared. The colour is not truly blue, it is the illusion of heat meeting distance. Through Webb's eyes, the palette shifts red infancy, becoming blue maturity. To imagine their brightness, replace our Milky Way with a blue dog, and the night sky would shine brighter than a full moon even at noon. Hundreds of stars born each second, a factory of fusion without rest. Yet creation carries its own ending. The dust that hides these cores also suffocates them. Radiation from newborn stars drives gas outward, halting new births. Within a few 100 million years, they will quiet, settle, spiral, becoming galaxies like ours. Evolution in the cosmos is not survival of the fittest, but transformation of the luminous. The bond between red infants and blue adolescents is more than visual. It is chronological proof that galaxies grow up, their metals rising, their dust thickening, their temperatures cooling. Still questions linger. Where are the missing stages between them? Models predict fleeting orange intermediates, but Webb has yet to find many. Perhaps those seasons pass too quickly for us to catch, or perhaps our instruments remain blind to their hue. Science breathes in these absences. The silence between data points is where imagination begins to build. Some propose that dust itself evolves early grains, absorbing light differently, painting youth redder than it truly was. Others caution that the resemblance may be coincidence, an echo of small samples. Yet the alignment of spectra persists a melody. The universe seems determined to repeat. You lean toward the monitor, tracing the luminous curves. They rise and fall together, two galaxies separated by eons singing the same note. Perhaps the paradox was never about speed, but about memory. What Webb captured is not error, but nostalgia written in starlight. When we look that far back, we're not merely studying evolution. We are participating in it. Every photon completes a journey begun when atoms first learned to combine. Observation closes the circuit between the universe that was and the one that now watches itself. So we listen to the harmony of red and blue, of birth and becoming. And as the data settles, another possibility flickers at the edge of thought, darker, stranger, unbounded by dust or starlight. The image of the quasi-star fades, leaving only the echo of its pulse. Light collapses into memory. Equations dissolve into silence. Yet from that silence, understanding begins to rise. If such beings truly existed, then the universe's childhood was more violent and far more creative than we ever imagined. For a century, cosmology has told a comforting story: galaxies formed first. Their stars lit the darkness. Black holes appeared later, gathering in their hearts. Orderly, predictable, almost human. But what if the sequence was reversed? What if gravity's first masterpiece was not light but hunger? This is the question now haunting the corridors of science. Data from James Webb continues to suggest massive ancient objects, luminous, too soon, too large for their age. The small red dots, the cliff, the silent cores, each whispering that the first structures in the cosmos may have been born not from fusion but from collapse. In this inverted timeline, black holes come first. They form within quasi-stars or by direct collapse of vast gas clouds. Around them, matter gathers, spirals, ignites galaxies, shape the way whirlpools shape rivers. Gravity becomes the artist, and the universe must be read from the inside out. Imagine the timeline as a ribbon of light stretched across the night. For generations, we traced it one way, from the Big Bang to stars to galaxies and finally to black holes. But Webb's light changes the flow. It asks us to read the universe in reverse, from black holes to galaxies to stars to life. In Los Alamos, researchers test this reversal through supercomputer simulations, universes inside machines, patches of space, only a few million light-years wide, evolving grain by grain. When early heavy black holes are included as seeds, the models suddenly reproduce Webb's luminous galaxies. The paradox dissolves. Numbers for once seem to listen, and yet the deeper we listen, the stranger the silence becomes. If black holes shaped galaxies who shaped the first black holes, the universe folds back on itself. Every answer births a deeper question. You can feel this tension standing at the edge of a revelation that rearranges everything familiar. It's like discovering that mountains are upside down, that rivers flow backward in time. The philosophical weight is immense. For ages we have linked light with birth, darkness with death. But the cosmos cares for neither symbol. In its first act, light and darkness were not opposites but partners. Gravity's void was the womb of illumination. Pause here, breathe. Outside your window, the night still glows with that ancient balance. The faint band of the Milky Way, the galaxy that shelters us, orbits a quiet leviathan, Sagittarius A, a black hole 4 million times the mass of the Sun. Around it, stars circle like fireflies around an invisible flame. Every glimmer, every dawn is an echo of collapse long past. In that sense, every sunrise on Earth is the memory of a fall transformed into light. The implications extend far beyond astronomy. If structure can rise from void, then creation itself may be a universal law, energy seeking symmetry, entropy weaving order before dissolving it again. The same rhythm builds planets from dust ecosystems, from chaos consciousness, from the noise of neurons. Collapse and creation are not rivals, they are phases of one eternal breath. Picture the early universe as an ocean. Quasi-stars are the whirlpools, black holes the draining currents, galaxies the foam left behind. Over billions of years, the ripples froze into filaments, the cosmic web spanning hundreds of millions of light years. The voids between clusters are immense, yet without emptiness nothing would hold. Even now, 85% of the universe remains invisible dark matter and dark energy, proof that absence has weight. Translate this to human scale. If the entire universe were the size of the Earth, all visible stars and planets would fit inside a single drop of water at its core. The rest, the unseen, would bind it all together. We live inside that unseen architecture every day. The Webb images remind us the cosmos is not a finished map but a living manuscript. Each observation edits the last line. We rewrite, erase, and rewrite again. Science is not the defense of certainty but humility before change. Perhaps that is the truest revelation. The universe evolves, and so must our imagination. You step outside the observatory. The wind smells of dust and iron. Above, constellations burn with steady patience. Somewhere among them lies the cliff, a red ember whispering the secret of beginnings. You raise your hand toward it. For a breath, the scale feels almost human. The space between your fingertip and that ancient light is the space between knowledge and mystery. And in that thin distance, wonder survives. We will keep building instruments, sending probes, chasing the earliest photons. But every time we peel back a layer, the lesson remains the same. The cosmos is older, stranger, and more self-aware than our equations allow. So let us pause before rushing forward. Let us listen to the silence left by the quasi-stars, to the quiet architecture of gravity shaping light. Somewhere in that silence lies the next question, and perhaps the next awakening. Because if galaxies were born from darkness, then maybe life is the universe remembering its first spark. And as that thought unfolds, our gaze turns homeward toward worlds of ice and hidden oceans where creation may still be repeating its ancient pattern in miniature. If galaxies were born from darkness, perhaps life too begins in the quiet, not among stars but under ice. From the vast to the microscopic, creation repeats its rhythm. And somewhere beyond the golden rings of Saturn, a small moon hides an ocean still singing that ancient tune. You are looking at Enceladus, one of Saturn's smallest moons, barely 500 kilometers across a sphere of frozen light. From afar, it seems simple, a pearl adrift among the rings. But beneath that glittering shell lies a secret that has changed how we think about life itself. For centuries, water meant Earth. Oceans were ours alone, blue, warm, certain. Then came Cassini. Launched in 1997, orbiting Saturn by 2004, it flew through the plumes erupting from Enceladus's South Pole fountains of vapor, stretching hundreds of kilometers into space, and tasted their chemistry. What it found was astonishing: salt organic molecules, microscopic silicate grains forged at nearly 90 degrees. 90 degrees means heat, and heat beneath ice means motion. Something stirs that hidden ocean tidal forces as Saturn's gravity pulls and kneads the moon, flexing its core like a heartbeat. Friction keeps the waters liquid. Motion feeds energy into the dark. Down there, vents may rise like underwater cathedrals. From their cracks, warm jets release hydrogen and methane into black water. No sunlight reaches this place, yet energy flows. On Earth, life thrives in such shadows, microbes feeding not on light but on chemistry. Imagine standing there beneath the crust in the dim pressure of alien tides. Towers of rock shimmer with mineral light. Bubbles drift upward like prayers. The ocean hums, softly echoing the rhythm that once shaped galaxies. To grasp the scale, Enceladus's ocean may hold more water than all Earth's lakes and rivers combined. Its icy shell, 20 to 30 kilometers thick, turns translucent in places, letting faint auroras shimmer through the frozen roof. Cassini's instruments, INMS for mass spectrometry. COS for dust analysis measured a mixture of water vapor, carbon dioxide, methane and ammonia. Together they form the habitability triad: liquid, water, organic matter and energy source. Enceladus has all three, and yet the story remains unfinished. Cassini could not see through the crust, could not taste the sea directly. It only brushed the spray at the moon's edge like tasting snow to guess the flavour of the ocean below. Still, that single sip changed everything. Picture a future mission. A silver probe dropped through a melt hole in the ice, drifting into the abyss, its light soft and patient. Crystals swirl past. Tiny particles shimmer, perhaps alive, perhaps waiting. The probe listens, records, transmits. Whispers from a world that has never seen the sun. Back on Earth, beneath our own sky, the thought humbles us. The distance is 1.4 billion kilometers, yet somehow it feels close, as if that alien sea were a mirror of our own, both holding warmth in the cold, both guarding the possibility of origin. That may be why Enceladus captures us so deeply. It is not just the science, the data, the molecules, the equations, but the echo of recognition water beneath ice light, beneath shadow life waiting in silence. The promise of a hidden sea is not a conclusion. It is an invitation. We have dreamed of an ocean beneath the ice, a living world hidden from the sun. But what if life, or at least its chemistry, never needed to hide? What if creation began not in the depths, but on the frozen skin of Enceladus, where light and radiation carve patterns invisible to the eye? You stand at the edge of the South Pole, the region astronomers call the Tiger Stripes. 4 great fissures stretch across the ice like luminous scars, each hundreds of kilometers long, each pulsing with vapor that glimmers in Saturn's dim light. For years, scientists believed these plumes carried the ocean's secrets: salts, silicates, organic molecules born in darkness. But new experiments whisper another possibility, one that turns the story inside out. In a laboratory on Earth, researchers built Enceladus in miniature water ice mixed with CO2, methane and ammonia, chilled to 200 degrees to then bombarded with high-energy ions to mimic cosmic radiation. Within hours, the ice changed colour, first pale yellow, then amber, then deep brown. Spectroscopic analysis revealed complex organics, amino acid precursors, long-chain hydrocarbons, molecules born not from warmth, but from impact. Radiation, it seems, can be an artist. Where we expect destruction, it paints potential. Picture this happening in real time on Enceladus's surface. Each day, charged particles from Saturn's magnetosphere rain upon the ice, their energy slicing through frozen carbon compounds. Over eons, new bonds form. Thin layers of organic frost build up parchment pages in a chemical manuscript. When tectonic forces tear open the Tiger Stripes, jets blast those layers into space, scattering fragments of molecular artwork across the black. Cassini's instruments, particularly INMs, tasted those plumes. It recorded methane-complex hydrocarbons, nitrogen-bearing molecules, but could not tell if they rose from the ocean below or from the ice itself. If the lab experiments are right, much of what Cassini tasted may have been surface-born, sculpted by radiation, rather than brewed by water. The implications are profound. For decades we've equated life's potential with comfort, with warmth, depth, protection. But perhaps harshness is the true cradle of invention. Imagine a layer of ice just 1 meter thick. Cosmic rays pierce it, each collision splitting molecules, generating radicals that reassemble into new forms. Over ages, the ice becomes an archive, a frozen history of molecular evolution. In 1 cubic meter, there may be more chemical variety than in an entire terrestrial glacier. The surface of Enceladus is in essence a natural particle accelerator and chemistry lab running for billions of years. At the Southwest Research Institute, scientists used ion beam accelerators to recreate that process. They detected formamide, a key intermediate for amino acids and nucleobases. Under UV and ion bombardment, formamide can yield adenine and uracil, the first letters of life's alphabet written in ice. Now imagine standing there yourself. The horizon glows faintly under Saturn's reflected light. Each step crunches through chemistry older than continents. Beneath your boots, invisible reactions unfold carbon chains, stretching, folding, reaching for structure. You're walking on a frozen symphony mid-note. Of course, not all are convinced. Radiation can create, but it can also erase. The dance between synthesis and decay is delicate. Yet Enceladus renews itself, its crust-cracking plumes erupting ice reborn. Creation and destruction chase one another in endless rhythm like waves on an unseen shore. On Earth, sunlight splits water to feed life. On Enceladus, cosmic light sculpts organics to feed possibility. Different energies, same intention to build complexity from simplicity. The more we learn, the thinner the boundary between living and non-living becomes. Molecules rearrange, form microenvironments in ice. Fleeting liquid films near fissure walls, thin as a hair melting for seconds, refreezing with memory. In those brief moments, chemistry takes one step closer to biology. You and I may never walk there, but we can imagine the first emissary, a robotic lander descending onto that luminous plane. Its drills hum softly, biting into the crust, drawing cores of layered ice. Inside, a spectrometer glows. Each peak on its display is a whisper from an experiment older than Earth itself. The data travels home 1.4 billion kilometers through the void and reaches antennas on a blue planet that still wonders if it is alone. When the first spectra arrive, scientists lean close eyes wide, not because they see life, but because they see possibility. The surface hypothesis does not replace the oceanic dream. It expands it. It tells us that life's chemistry may not need comfort, only opportunity. Radiation, cold time, not obstacles but instruments. Perhaps Enceladus teaches the humblest truth of all: the universe builds meaning wherever energy can flow, even through a fracture of ice. The idea that radiation could sculpt the first molecules feels almost poetic. We are tempted to call it proof, to say that Enceladus has given us life itself. But science has no temples, only thresholds. Every discovery opens another door, and beyond it waits not certainty but more questions, patient, infinite. Hope is a beautiful instrument, but it must be tuned. In the silence after Cassini's final transmission, scientists stared at its last image, the pale curve of Saturn's rings fading as the spacecraft dove into cloud. Data ended, longing did not. Cassini had given us oceans under ice plumes of chemistry, whispers of possible life, but not the one answer we wanted most. We wanted confirmation, not possibility. But the cosmos rarely grants closure. Picture it: the spacecraft no larger than a bus falling silently through gold and storm, its instruments burning its memory already halfway home. Within that stream of bits, spectra densities, ratios lay both triumph and restraint. Cassini found methane, carbon dioxide, ammonia, silicates, salts, organics, but no cells, no metabolism, no clear signature of life. So where does that leave us? Between two hypotheses balanced like light on water. The oceanic model still stands strongest, a vast hidden sea warmed by Saturn's pull hydrothermal vents, breathing gradients of energy. It gives us a blueprint for habitability. The surface radiation model, newer and bolder, reminds us that chemistry can thrive in exposure, that a frozen canvas can host its own long experiment in time. Perhaps both are true. Perhaps organics form in the ice, then fall into the ocean, a collaboration between darkness and light. Still between theory and proof lies distance 1.4 billion kilometers and at least a decade of waiting. The next chapter is already imagined: the Enceladus Orbolander, planned for the 2030s to hover to land to taste the plumes directly. It will search for amino acids, lipid-like molecules, isotopic ratios that separate biology from geology. Yet even that mission may not bring finality. It may simply trade one mystery for another, as all good science does. And perhaps that is the lesson we keep resisting. We want a universe eager to reveal itself, but it may be more patient than we are. When Galileo first turned his telescope to Jupiter, he saw 4 moons and thought he'd found perfection. Now we know those worlds carry oceans, volcanoes, storms that last centuries. Knowledge expands, certainty contracts. Stand beneath a clear night sky. Saturn's light takes over an hour to reach you. In that hour, data travels, interpretation shift, humility grows. Somewhere under those rings, Enceladus breathes, exhaling dust salt fragments of organic snow, scattering them like prayers no one can yet translate. We speak of searching for life, but perhaps what we truly seek is reflection. To find life elsewhere would mean we're not alone. To find none would mean we are rare and precious beyond measure. Both answers are sacred. So we hold our hope carefully, not extinguished, but steady like the pilot flame of curiosity. Imagine the moment when a future probe sends home a droplet of Enceladus's water caught in starlight. Inside that droplet, perhaps only chemistry, perhaps more. The signal will arrive, faint, delayed, shimmering through static. There will be silence in every control room, not celebration, not disappointment, only the quiet awareness that we are listening to the universe think out loud. Hope tempered by patience becomes wonder without demand. That is what science asks of us: to love the unknown, not for what it confirms, but for what it reveals about ourselves. As you drift in thought, picture that frozen world again. From Saturn's orbit, it is no larger than a bead of ice. Yet beneath its crust, oceans move vents, breathe molecules, rearrange. It is both alive and lifeless, both known and waiting. The ocean beneath Enceladus closes behind us, silent as thought. We have searched for beginnings, now we turn toward endings. Because even dying in the universe is a kind of creation. Far beyond our solar system in the faint constellation Sagitta the Arrow, there is a star preparing to die. Its name is V Sagittae, or simply VSGA. To the naked eye, it is nothing more than a speck of light, a pinprick among billions. Yet within that point burns one of the most volatile relationships in the galaxy, a binary system locked in a fatal dance. VSG is not one star, but two: a white dwarf and a massive blue companion orbiting so close that the space between them is smaller than the gap between Earth and the Moon. The blue star is losing itself, bleeding hydrogen toward the dwarf, a bridge of plasma spanning the void, a luminous thread of devotion and decay. You can almost picture it, one star shining too brightly, the other quietly consuming it, love and gravity fused into destruction. Astronomers have watched this duet for decades. Every few years it flares, brightness surging as the dwarf devours fresh fuel. These outbursts are warnings, the balance is shifting. The white dwarf grows heavier, edging toward its limit, 1.4 solar masses, the Chandrayaan boundary, the point beyond which physics itself collapses. When that threshold is crossed, the star will fold inward for a heartbeat, then erupt outward with unimaginable force. The result, a Type Ia supernova, a thermonuclear flash visible across galaxies. Type Ia supernovae are the universe's standard candles, so precise in brightness that we measure cosmic distance by their light. Each one means the same thing: a white dwarf reaching its limit, annihilating itself in perfect symmetry. If predictions hold, VSG may reach that moment within a century, perhaps even within our lifetimes. When it happens, it will outshine the entire Milky Way for days, bright enough to cast shadows on Earth, luminous as the moon itself. Imagine walking outside at midnight and seeing not one moon but two, a pale circle above and a blue-white echo beside it, pulsing like the breath of a dying god. When that day comes, telescopes across the world will turn their gaze, and every detector optical radio gamma ray will listen to the death song. For a brief moment, the universe will write in light what it cannot say in words. But endings in the cosmos are only beginnings in disguise. A Type Ia supernova does not simply destroy, it forges. In its shockwave atoms of iron, nickel, calcium are born the elements that build planets, oceans, and breath. Somewhere in that expanding dust, a future world will form, carrying fragments of that final heartbeat. Look at your hands. The calcium in your bones once burned in a star like VCG. The iron in your blood once cooled from such a fire. So when we say VSG is dying, what we really mean is the universe is preparing to give again. Still, it is impossible not to feel awe at the violence of it. The total energy released in that single detonation will equal the sun's entire lifetime output compressed into a few days. 1 billion Earths could fit inside that storm of light, and still it would burn. Standing beneath the night sky, you might feel a tremor of humility. Somewhere out there, a star is gathering its final breath. It does not know we are watching. It does not need to. When it goes, it will inscribe across the dark one of the oldest truths in existence, that every end is a seed. While one star prepares to vanish in brilliance and another kind of shadow prepares to pass by us. From the grand explosion of a dying sun to the quiet approach of a single rock, the scale changes. You stand beneath the night sky in April 2029. The air is still. Above the western horizon, a moving point of light brightens with every heartbeat. It is not a star. It is Apophis, a mountain of stone 340 meters wide, spinning through space at nearly 30 kilometers per second. For years, its name has carried the echo of myth. In ancient Egypt, Apophis was the serpent that tried to devour the sun each dawn. Now it carries another kind of hunger, the possibility of collision. When it was discovered in 2004 at Kitt Peak Observatory, calculations gave a chilling probability, nearly 3% chance of impact with Earth in 2029. That number has since dropped to 0, but the approach remains historic. On April 13, 2029, Apophis will pass only 37,000 kilometers from Earth's surface, closer than our geostationary satellites. In astronomical terms, that's a whisper. Imagine tracing that distance in your mind, 37,000 kilometers, barely 3 times Earth's diameter. If the planet were a basketball, Apophis would skim its surface less than a centimeter above it, close enough to feel gravity's breath. Through telescopes, it will appear as a bright moving dot, visible even to the naked eye across Africa and Western Europe. More than 2 billion people will look up different continents, one shared motion of light. What will they feel? Or perhaps, or something deeper, that ancient reflex of fear buried in the species since the first stone fell from the heavens. Because Apophis will not simply pass, it will curve as it goes. Earth's gravity will tug at its orbit, bending its path by thousands of kilometers. A slightly stronger pull, a fraction of a second's delay, and the serpent's trajectory could shift in ways we barely control. Scientists call this the gravitational keyhole, a narrow corridor of space only a few hundred meters wide, where if Apophis passes precisely through Earth's pull, would set it on a collision course for its next return in 2068. It will not happen this time, but the fact that it could tells us something essential. We are no longer merely observers of the cosmos, we are participants in its choreography. Picture the years leading up to that night, the Goldstone radar array mapping the asteroid's spin, the archived Arecibo echoes like heartbeat traces, teams at NASA's Planetary Defense Coordination Office simulating millions of possible paths, satellites watch, computers refine. Humanity for once faces the universe not with ignorance but with readiness. Apophis itself is a strange world, a mosaic of dust and fractured rock, its density revealing a rubble pile, not a solid mass. If you could stand on its surface, your steps would stir pebbles that would take minutes to fall back. Gravity there is so weak you could leap hundreds of meters in a single bound. Its day lasts less than 30 hours. It tumbles through sunlight like a coin flashing with iron and nickel glints. The year 2029 will mark the first time in history an asteroid of this size passes so close, witnessed in real time by billions. For a few minutes the world will share the same sky. You can almost hear the hum of humanity holding its breath. Somewhere in a backyard observatory, a child will trace that point of light through a telescope the way Galileo once traced Jupiter's moons. For that child, Apophis will not be a threat but a mirror, a reminder that our planet is small, our vigilance fragile, our imagination vast. And yet beneath the beauty lies precision. A miscalculation of only tens of seconds could have rewritten the story. The Earth's rotation, the moon's pull, even the faint heat of sunlight all nudge the asteroid's course. That is the scale of our luck, not divine but mathematical. From afar the event will look serene, but the forces beneath it are colossal. Gravitational interactions strong enough to shift satellites, tidal stresses stretching the asteroid's shape as it passes. Some fragments may even break free, forming a faint glowing tail as it retreats. And when it's gone, the world will exhale. Astronomers will celebrate, headlines will call it the day the sky moved. But the lesson will linger, the border between safety and catastrophe is thinner than imagination. Apophis is not an omen. It is a rehearsal for the day when another object less forgiving traces the same corridor of space. That is why we send missions like DART to test if a small push, a precise impact, can shift destiny by a fraction of a degree. Because in orbital mechanics, a fraction today means salvation tomorrow. So when the night of April 13th, 2029 arrives, step outside, look up. Find that moving spark between the stars and the satellites. That is the serpent of light sliding through the gap between what we know and what we fear. It will pass, and the darkness will remain unchanged. Apophis passed and the world exhaled. But its shadow left a question hanging in the sky. What if next time the orbit bends just a little differently? In 2022, humanity attempted something it had never done before, not to study the heavens, but to change them. The mission was called DART, the Double Asteroid Redirection Test. A small spacecraft no larger than a vending machine launched from California on November 24th, 2021 with a single purpose: to crash. Its target was Dimorphos, a moonlet orbiting a larger asteroid called Didymos, roughly 11 million kilometers from Earth. The goal was not destruction, but persuasion, to test whether a deliberate collision could alter an asteroid's orbit by even a fraction of a percent. Because in the mathematics of survival, fractions matter. Imagine standing in mission control on September 26, 2022. On the screen, the target grows from a speck into a rugged, sunlit world. Voices murmur countdown, steady, reverent. Then the image freezes, signal lost. Impact confirmed. A cheer rises, not for destruction, but for precision. DART struck Dimorphos at 22,130 km per hour, delivering the energy of about 3 tons of TNT. The impact carved a crater and launched a plume of dust nearly 10,000 kilometers long. When astronomers measured the orbit afterward, the results astonished. Dimorphos's period shortened by 32 minutes. A celestial body 160 meters wide had been nudged imperceptibly to the eye, but profoundly in meaning. It was the first time in history that humanity had changed the motion of another world. Picture it: a speck of metal striking a drifting mountain, and that mountain shifting its rhythm like a heartbeat, skipping once in the music of the cosmos. The lesson was clear. Deflecting an asteroid is possible, but only if we act early and only if we strike true. Later analyses by the Johns Hopkins Applied Physics Laboratory and the European Space Agency's HERA mission team revealed a deeper truth. Angle matters. A strike too steep and debris absorbs the energy. Too soft and inertia swallows the push. A miss of 10 degrees could mean the difference between salvation and futility. Planetary defense is not about power, it is about geometry. Think of it this way. A delay of 1 second in launch or a fraction of a millimeter in trajectory translates into thousands of kilometers at target. It is a dance between time, space, and gravity. Humanity is learning to choreograph that dance one orbit at a time. Now scale that idea forward. A rock 500 meters wide emerges from the dark something larger than Apophis. We detect it decades early. A fleet of impactors launches descendants of DART propelled by solar sails and ion thrusters. They strike not with explosions but with patience momentum delivered gently across millions of kilometers. Each impact shifts the orbit by mere centimeters per second. Over years that drift multiplies. The rock passes harmlessly by. No single collision saves the Earth. Collective foresight does. The concept is simple, but the discipline it demands is immense. It requires not only technology but humility, the understanding that our world can be protected only through cooperation that transcends borders and centuries. Because unlike nations or languages, asteroids obey only gravity. Somewhere beyond Mars, the dust from DART's impact still drifts tiny fragments of a human gesture, our first attempt at self-defense written in cosmic dust. And when Hera, the European follow-up mission, arrives at Dimorphos in 2026, it will orbit the scar left by DART, mapping the crater, measuring density, studying the transfer of momentum in exquisite detail. Each data point will refine our aim for the next time the sky throws a stone. There is symbolism in this. For the first time, the universe has noticed our reflex. We are no longer passive witnesses of celestial fate. We are participants, apprentices of motion. Yet power demands perspective. To move one rock is to tug on one thread in a web that spans eternity. Each decision echoes through orbits we cannot yet trace. The triumph of DART lies not in its collision but in its restraint in learning when, where and how not to strike. Look up tonight. Somewhere among the stars, Dimorphos still circles Didymos, its path a little shorter, its rhythm forever changed. The first world to feel the weight of human intention. And perhaps when the next Apophis comes, our descendants will not look up in fear, but in quiet confidence, knowing we have learned to move with the heavens, not against them. We have learned to deflect stones from the heavens, yet we still do not fully understand the stones that made us. Beneath the triumph of protection lies a quieter mystery, not of motion but of matter. Something is missing in the chemistry of creation. Silicon, the quiet architect of worlds. On Earth it builds continents and glass mountains and microchips the mineral skeleton of civilization. In theory it should be everywhere. Every planet, every gas giant, every star born from the same nebula dust should carry its spectral fingerprint. And yet, when astronomers look into the atmospheres of the giant planets, Jupiter, Saturn and their cousins, the brown dwarfs, something essential is missing. The lines that should belong to silicon, those subtle dips in infrared light, are gone. The element that built Earth's crust has vanished into silence. Picture the scientists at their consoles, eyes fixed on the data streaming from the James Webb Space Telescope. Spectra unfold like songs, each wavelength a note, each element a chord. Hydrogen sings, helium hums, methane glows in faint blue. But where silicon should play its tune, there is only quiet. Why? By every model of planetary formation, silicon should be abundant. When the early solar system condensed from dust, silicon and oxygen were among its most faithful companions. They should mix freely with hydrogen in the outer planet's atmospheres. And yet, even with Webb's exquisite sensitivity able to detect carbon dioxide at billions of kilometers, the spectral fingerprints of silicate compounds remain absent. At first, scientists blamed instrumentation error. Perhaps the lines were drowned in methane or buried beneath ammonia's glare. But as data accumulated from Keck, from VLT, from Spitzer's fading archives, the silence persisted. The mystery solidified the missing silicon problem. Imagine standing on Jupiter's upper cloud deck, storms of ammonia ice and water vapor swirling below your feet. Deeper down beyond any probe's reach, temperatures climb past 1,000 degrees. Their silicates should condense into mineral snow quartz, olivine pyroxene rising and falling like ash in a volcanic sky. But telescopes see none of it. It's as if the element has been buried too deep to breathe. One hypothesis: gravitational segregation. Silicon reacts with oxygen to form heavy silicate oxides that sink below the visible layers pulled down by the giant's immense gravity. These compounds, denser than water or methane, may have settled into the unseen depths, forming part of the rocky hearts of Jupiter and Saturn. In that case, the element isn't absent, merely out of reach. Another idea: chemical sequestration. If early Jupiter formed in an oxygen-rich cradle, most silicon could have bonded into silica SiO2 early on, leaving its upper layers hydrogen-dominated and silicon poor. In that case, every giant planet carries the chemical accent of its birthplace, a fossil record of temperature, pressure and oxygen ratio frozen into its atmosphere. Still, the evidence feels incomplete, and so astronomers turn their gaze outward to the brown dwarfs, those failed stars bridging the gap between planets and suns. Massive enough to fuse deuterium but not hydrogen, they preserve the chemistry of ancient nebulae, living fossils of the galaxy's youth. If silicon is missing there too, the mystery deepens beyond our solar system. Picture the scene: Webb's NR-spec instrument aimed at a faint brown dwarf, its light stretched by distance and time. The spectrum scrolls across the monitor. Carbon monoxide, methane, water vapor, but still no silicon. Perhaps the atmospheres are too heavy, binding silicon into molecules that never rise. Or perhaps those ancient stars were born when oxygen was scarce, when hydrogen ruled the chemistry of creation. The deeper implication hums beneath the data. What if the missing silicon isn't an absence, but a memory? A trace of the universe's earliest poverty when stone itself had not yet learned to form? That question leads to a single strange object, a brown dwarf so old its light is stretched by 12 billion years of history. It was discovered not by a space agency, but by an amateur astronomer staring at his computer in the quiet hours of the night. He called it the accident, and through it the silence of silicon will finally begin to speak. The search for silicon's missing voice led nowhere until one night the silence was broken, not by a billion-dollar telescope, but by the hum of a home computer. In a universe ruled by stars, sometimes it takes a single human curiosity to make the cosmos speak again. He wasn't supposed to find it. Dan Cassini was not an astronomer, just a software developer with a fascination for the faint things between stars. Most nights after work, he logged into Backyard World's Planet 9, a citizen science project that let volunteers sift through data from NASA's WISE infrared telescope. The task was simple: compare thousands of flickering frames pixel by pixel, watching for a light that moved when the background stayed still. Monotonous, meditative, like listening for a heartbeat beneath noise. One evening in 2020, Cassini noticed something odd. A faint point of light shifted between frames, too slow for an asteroid, too dim for a star, too cold for anything familiar. He almost ignored it. Then he saw the color profile. It didn't match any known brown dwarf. He flagged it, typed a note: possible outlier spectral anomaly. At Caltech, the team reviewed the data. The coordinates pointed to a tiny invisible wanderer drifting through the constellation Hydra, roughly 50 light-years away. Its infrared spectrum implied a temperature of only 250 Kelvin, about 20 degrees colder than dry ice. In stellar terms, it was practically frozen. They called it the accident, because statistically it should not exist. Most brown dwarfs, objects heavier than Jupiter, but lighter than the smallest stars, cool and fade in predictable ways as they age. But the accident refused that pattern. Its light was too bright in some wavelengths, too dim in others, as if it carried two contradictory ages, both ancient and young. For months, observatories tried to classify it. Keck, Gemini, North, even Spitzer before its retirement all took spectra. None made sense. Then came JWST with its NIR-spec instrument capable of peeling light molecule by molecule. And there, hidden in the infrared bands near 4.6 microns, appeared a signature no one expected: lines belonging to monosilane CH4. Silicon at last was speaking. Monosilane is fragile. In oxygen-rich air it oxidizes, instantly vanishing into silica. Its presence meant one thing: an atmosphere poor in oxygen, rich in hydrogen chemistry from the universe's youth. The detection implied the accident formed when stars were few, when cosmic gas still carried the elemental simplicity of creation. Picture the moment the spectrum appeared. A thin curve, rising, dipping, rising again, a heartbeat stretched across 12 billion years. For a breath the scientists were silent. Then someone whispered, "It's real." If that holds, the accident may be among the oldest substellar objects ever found, 10 to 13 billion years in age, born when the Milky Way was still forming. Its existence bridges two eras, the hydrogen-helium dawn and the metal-rich present, and it was discovered by someone watching from his living room. Cassini's find reshaped how astronomers viewed citizen science. Projects like Backyard Worlds no longer looked like games, but like distributed telescopes, the collective vision of a species learning to see itself. That an amateur could uncover an object carrying the chemical memory of the first stars, humbling and profoundly poetic. Still, the accident raises as many questions as it answers. If its atmosphere truly contains monosilane, perhaps silicon behaves differently under ancient conditions. Maybe early brown dwarfs formed before oxygen had filled the interstellar medium, allowing silicon to bond with hydrogen instead. Such chemistry would have vanished once the first supernovae enriched space with heavier elements. That means the accident is not merely a relic, it is a time capsule, a window into a chapter of the cosmos we can no longer witness directly. Picture it: a dim ember adrift in darkness, its light stretched thin by age, its spectrum whispering forgotten chemistry. If you could stand beside it, though you never could, the glow would be soft enough to gaze upon bare-eyed, a copper ghost against black infinity. A single world wandering since the dawn of the galaxy. Scientists plan follow-ups. JWST will return. Ground observatories will refine parallax and measure its motion in exquisite detail. Each photon adds another line to a story begun accidentally by one curious human being, and somewhere Dan Cassini still checks the data stream, scrolling through endless frames, listening for another whisper in the dark. There is something profoundly human in that image, one person alone at a screen searching for movement among the stars. It echoes the same patience that guided Cassini to Saturn and Dart to a distant asteroid, the same quiet instinct to notice. A single act of attention linking our fragile world to the universe that made it. The accident had spoken in light a pattern of hydrogen and silicon that should have been impossible. And yet the more scientists looked, the more it seemed that this impossible pattern was the most ancient language in the universe. It was as though the cosmos itself had left behind a trace and memory of how it once thought before oxygen filled the stars. Imagine being there at the beginning. There is no blue, no oxygen, no stone. Only hydrogen drifting through the warm haze of creation, the universe still glowing with its first heat. Somewhere in that darkness, silicon atoms float freely, unable to find oxygen to cling to, so they choose hydrogen instead. They form fragile bonds, light molecules called monosilane, invisible, short-lived, but perfectly suited to that primordial world. It is chemistry before weather, before rock, before life, the first gesture of structure in the void. Billions of years later, a small telescope orbiting the Sun catches a whisper of that era. In the spectrum of a dim brown dwarf light bends at the same frequencies monosilane would leave behind. The reading is delicate, almost impossible, a signal buried beneath noise, and yet when the data are checked again and again, the shape of the curve remains. No one expected to see this molecule, not here, not now. The only way it could survive is if the accident had formed before the universe was rich in oxygen. Its very chemistry is a fossil, in that single observation the past and present touch. It means that silicon, the backbone of Earth's crust, once moved through space as vapor bound to hydrogen drifting through the hydrogen sea of early time. And when the first massive stars exploded, they filled the universe with oxygen, changing the rules forever. From then on, silicon would become stone hidden deep inside planets. But the accident older than that transition kept its original memory intact. The idea changes everything. If matter can preserve the atmosphere of its birth, then chemistry becomes a map of time. Every planet, every brown dwarf, every grain of dust carries the ratios of hydrogen and oxygen that surrounded it when it was born. Even the colour of a world becomes a kind of diary entry, a story about temperature, pressure and age. The accident then is not simply a strange brown dwarf. It is a chapter from the childhood of the cosmos written in molecular handwriting. Back home in our own solar system, the giants Jupiter and Saturn still puzzle us. Their atmospheres glow with ammonia, methane and water, but silicon remains hidden, locked away in silence. The chemistry of their birth explains why they formed later in a nebula, already saturated with oxygen. There, silicon could not stay light. It turned to silicate rock, dense and heavy, sinking deep below the visible clouds. The planets we see today are monuments to that chemical maturity. Oxygen had become the ruler, hydrogen the servant. Where the accident floats with memory, Jupiter hides its own beneath thousands of kilometers of cloud and pressure. And yet the difference between them is not one of kind, but of time. One remembers youth, the other age. Silicon, like a storyteller, changes its voice depending on the era it speaks from. Scientists now call this concept the hypothesis of chemical memory, the idea that matter itself can remember the environment it was born into. Each atom carries a record of its first surroundings, the balance of gases, the intensity of starlight, the rhythm of creation. In this way, chemistry becomes a kind of language for time. Each molecule, a verb, each bond, a fragment of sentence written in the physics of its age. If this is true, then every element has a biography. Hydrogen remembers the dawn of everything. Oxygen remembers the first fires of stars, and silicon remembers the bridge between the two, the moment when the universe cooled enough to build structure but before it learned to breathe. You can imagine the researchers standing before the data screens, the pale green lines of spectra stretching like a musical score. They are not just analysing, they are listening. Each curve is a whisper from a molecule older than galaxies saying, "I have seen the beginning and I have not forgotten." It is a strange kind of archaeology, one that digs not through soil but through light. And then the implications unfold. If matter keeps its chemical memory, then everything around us is a witness. Every planet is an autobiography written in elements. Every stone and cloud is an echo of a different epoch. Even we built from these same atoms are records of those ancient transformations. The glass in your window, the silicon chip inside your device, the minerals in your bones. All of them are fragments of an elemental story that began long before Earth existed. The chemistry that gives us thought is also the chemistry that remembers. Perhaps that is why discovery feels so strangely intimate. When we study the accident, we are not looking outward, but inward, back toward the source of our own materials. It is not only about the element we cannot see, it is about the realization that we are made of the same forgetfulness and remembrance. Matter forgets quickly, but light does not. And when we measure light, we awaken the memory within matter. The scientist who first saw the signature of monosilane said it felt almost human. Something that delicate, that fleeting, had survived the fires of time just long enough to be noticed. Like a message written in frost before the sunrise. The molecule would not last forever in oxygen-rich space, it would soon vanish. But for that brief moment it existed as proof that the universe keeps records. And perhaps in that quiet fact lies a larger truth. The universe does not archive its history in libraries of stone or language, but in the chemistry of its own breath. Every reaction, every bond, every spectrum is an entry in its endless journal. The accident gave us a page. We turned it and found our own reflection. So the missing silicon was never missing. It was simply hidden in another chapter of time encoded in a different dialect of matter. We did not discover it, we remembered it. And through that remembering, we learned again what the universe has been saying since the first atoms met in the dark. Silicon remembered the dawn, and through it so did we. From a single molecule in the light of a forgotten star, we began to understand that the universe is not silent, it is reflective. Every discovery, every experiment is the cosmos thinking about itself through our hands. There is a quiet irony in how far we've come. For centuries we looked outward, searching for patterns in the light of Jupiter, the glow of supernovae, the shadows of Enceladus. But with each measurement, with every pixel caught by James Webb Space Telescope, we've been slowly tracing not just the shape of the universe, but the outline of our own curiosity. Imagine you're standing before the giant golden mirror of Webb itself, 6.5 meters across, floating 1 million miles from Earth. Every hexagon of that mirror is aligned to nanometers so precise that if it were the size of a football field, its seams would be thinner than a strand of hair. And yet what it reflects is not just galaxies, it reflects the human question. What are we made of, and what remembers us science has become a mirror. Each new equation, each observation bends back toward the observer. When we point a telescope at the accident, we're not only looking at a brown dwarf 50 light-years away, we are looking at the first chemical pages of our own origin. When we send a probe through the icy plumes of Enceladus, we're not only searching for amino acids, we're searching for an echo of ourselves, a version of life written in another alphabet. You can feel that strange duality. We study the stars to understand nature, and yet nature uses us to understand itself. Our instruments are its nervous system. Our questions are its thoughts taking form. Think of the Voyager probes still drifting in interstellar space, their metal skins dusted with cosmic rays, their recordings of back and heartbeat still pulsing silently outward. They are no longer machines of exploration. They are memories carrying traces of us into the dark, like neurons extending from a universal mind. The laws of physics, gravity, thermodynamics, entropy seem impersonal at first. But as we refine them, they reveal something tender, a universe capable of self-awareness through pattern. The hydrogen that fuses in the heart of the sun is the same hydrogen that runs through our blood. When it burns there, it warms us here. And when we think about it, the universe completes a circuit energy turning into thought, thought turning into recognition. You can picture it: a photon leaving a quasar 10 billion years ago, strikes a sensor in Webb's mirror tonight, and through that single impact a human mind imagines how space once looked before galaxies formed. Across all that time and emptiness, a line of awareness connects. Not technology, not even light, awareness itself. Perhaps the same awareness hums beneath the magnets of a particle accelerator as protons collide and vanish into equations. Perhaps every experiment is a kind of meditation matter, asking itself what it means to exist. And maybe that is what science has become, not just the search for truth, but the act of reflection, a ritual where curiosity meets its own shadow and calls it wonder. The discoveries of this century, the red dots of early galaxies, the chemical ghosts inside the accident, the faint traces of silicate rain buried within Jupiter's storms, they all point to the same secret, that the universe is not merely expanding outward, It is folding inward too, turning perception back upon itself. Every photon we catch is both information and invitation. Every formula written on a whiteboard is a mirror tilted toward the infinite, and perhaps that is why when we listen to the hum of data, when we hear the signal rise above the cosmic background, we feel something familiar. Not alien, not distant, but intimate, like the sound of our own breathing magnified by eternity. Science does not separate us from the universe. It reunites us with it. It is the language the cosmos invented so that it could describe itself to consciousness. So when you next gaze at the stars, remember they are not beyond you. They are within you, reflected in every atom of silicon, every drop of hydrogen, every question that dares to rise from the dark. And if you listen closely in that thin pause between thought and awe, you might hear it, the universe exhaling through you as it remembers its own name. There comes a point in every journey of discovery when knowledge bends back into mystery. The closer we come to the truth, the more it dissolves like starlight scattered by interstellar dust. And perhaps that is what the universe has been teaching us all along, that to truly understand it, we must learn to not know. Think of James Webb floating in its orbit around the Sun-Earth L2 point, its mirrors catching light that has travelled for more than 13 billion years. That light began its journey before galaxies fully existed, a photon born in chaos, now ending in the curve of human curiosity. But even as it arrives, it refuses to answer everything. The images Webb sends us a breathtaking yes, but each one replaces one question with 100 more. You can imagine the scientists watching those first images unfold, the deep field crowded with ancient galaxies, each smaller than a grain of sand in the frame, some red, some blue, some stretched into arcs by gravity. And among them, the strange red dots that shouldn't be there at all. Too massive, too old, too bright for their place in time. They are paradoxes, and paradox is the universe's favourite language. We name these things because naming helps us see. We call them quasi-stars, early galaxies, blue dogs, supernova candidates, chemical anomalies, but in truth those are placeholders for our confusion. Each term is a bridge suspended over the unknown. Science at its heart is the art of walking that bridge without pretending the other side is solid ground. When we don't know, we look harder. When we can't see, we build mirrors, launch satellites and send machines like DART to touch distant stones. And yet the further we go, the more the horizon moves. We discover dark matter, then dark energy, and now more than 95% of the universe is something we cannot describe. Our greatest measurement has become an admission. Most of reality is invisible. But maybe that invisibility is the point. Maybe the cosmos keeps a part of itself hidden, so that consciousness has something to chase like a horizon that ensures the traveller never stops walking. Because what would a universe without mystery even be? A static painting, a story without turning pages. Every unanswered question gives us movement. Every silence invites another instrument into the cosmic orchestra. We are guided not by certainty, but by its absence, a gravitational pull that draws thought forward through time. Look at Enceladus, its icy crust glowing faintly in Saturn's reflected light. We found evidence of amino acids in its plumes, but when we ask, is there life beneath the ocean, answers with silence. Silence too is a kind of response. It tells us to listen deeper, to wait longer, to see the difference between stillness and absence. And that lesson echoes across everything we study. The accident whispered chemistry older than oxygen. Visquet promises a future explosion we may never witness. Each phenomenon gives us a glimpse, not a conclusion, an unfinished thought left drifting between epochs. We are not meant to master the universe. We are meant to listen to it, to live inside the tension between knowing and not knowing. You can picture it standing beneath a night sky so clear that the Milky Way arcs above you like a bridge of frost. You raise your hand, trace the constellations, and realize that every point of light you see is already gone. The light from VC, that future supernova, left its star thousands of years ago, and by the time it reaches us, the explosion will already have happened. You're not watching the universe now, you're watching it remember itself. That's the paradox: the further out we look, the further back we see. Every telescope is also a time machine, and every observation an act of humility. We're always looking at what was never at what is. So maybe learning to not know means learning to stand inside that delay, to live comfortably between question and echo. We are not separate from uncertainty. We are made of it. The atoms in our bodies were forged in stars whose deaths we still cannot predict. Even silicon, the quiet element that built our machines, was once part of a molecular fog that forgot how to shine. And yet here it is, remembering through us, powering our telescopes, our computers, our thoughts. What then is ignorance if not another form of connection? When we say "I don't know," we're not stepping away from truth. We're stepping closer to its horizon. We become participants in the universe's unfinished sentence. To not know is to keep the mystery alive. It is to let the cosmos continue its story through us. It is to stand before a mirror of gold and see not a reflection, but a question. Science never really ends with answers, it ends with perspective. We began this journey asking questions about Enceladus and its buried ocean, about the strange red dots that seem to defy the timeline of galaxies, about the missing silicon that disappeared into the hearts of giants. And in the end, what did we find? Not certainty, but reflection. Every discovery, every hypothesis was less about conquering the unknown and more about learning how to stand inside it. That was the quiet message of this long exploration, that the act of wondering is itself an act of creation. You can feel that realization settling now like dust after a supernova. The accident found by an amateur astronomer in the stillness of his room was not just a point of light, it was a reminder that the universe speaks through anyone who dares to listen. Jabba floating beyond Earth's shadow, showed us galaxies too young and too heavy to exist, forcing us to rewrite the story of beginnings. Enceladus, whispering its icy plumes into space, reminded us that life might bloom even in silence. And Dart, crashing into a rock millions of kilometers away, taught us that we are not helpless observers. We are part of the cosmic choreography. The lesson beneath all these discoveries is simple: to know the universe, we must first learn to question it, and sometimes to question even our own questions. Maybe that's what science really is, a dialogue between what is and what might be, a conversation between starlight and curiosity. You can imagine the scene, the hum of data fading, the last light from JWST's mirror, glinting like a pulse. In control rooms and quiet offices, astronomers close their laptops, students stop scrolling through spectra, and for a moment the world feels still. But the stillness is only apparent. Even now, particles move, photons drift, and gravity continues to write its invisible script. Somewhere another person might be staring at a new anomaly, a point of light that doesn't fit a line on a graph that won't stay straight. And from that small act of attention, the next chapter of the cosmos may begin. So what do you think now that the light has dimmed? What if all our theories, all our instruments are just ways for the universe to think out loud through us? What if our curiosity is the echo of its first explosion, still rippling through space, still seeking form? The universe never truly sleeps. It only changes the shape of its dream. In the dark among the ancient waves of microwave light, photons still drift slow, steady like breathing. And we, these temporary beings, borrow that light for a little while to think, to wonder, and at last to rest. Every hypothesis is a lullaby, every question a soft wind moving through the mind. When you close your eyes, you're lying within billions of years of light, surrounded by every possibility the cosmos has ever imagined. Sleep now, because even as you dream, the universe is still telling its story through you.